Hello and welcome to the second video of my series how to customize scikit-learn. Today we are going to talk about creating predictors or models and transformers. Basically we are talking about how we can use inheritance from mixins, so multiple inheritance, in scikit-learn to create even more competent classes. First, let's have a small recap. Last time we talked about superclasses and subclasses. Basically, one class can inherit functionality from another one. This other class is called the superclass, while the class which you use the inheritance in is called the subclass. In scikit-learn, this concept is used quite often. Most importantly, maybe, with the base estimator. The base estimator helps you to implement your own estimators by just inheriting from it. You don't have to do that, as scikit-learn uses duck typing, but it is recommended. So in here, you only have to implement the initialization method as usual and the fit method, and then you get the set params and get params for free. Today we are going to talk how multiple inheritance, or more specifically mixins, are used in scikit-learn. So let's talk first about the concept of multiple inheritance. Multiple inheritance basically just means that you have one subclass inheriting from multiple superclasses, so it has multiple inheritance. This concept can get a little bit tricky, especially if you have the same variables or methods inside of both superclasses. So please be aware that you have to be careful when doing these things on your own. But in scikit-learn, these concepts were simplified by using so-called mixins. Mixins basically means that you only have very specific functionality in a second superclass, which is added to something like a base class. So in general, it looks a little bit like this. You have the base estimator providing you the usual functionality for scikit-learn. This makes everything an estimator. The transformer mixin assumes already that you have a base estimator, so an estimator, but it adds everything which is only important for transformer mixins and only specific for them. So it will not implement the fit method, it will not implement get param and set params, as these are already in the base estimator. But what it will do is help you, for example, to create a fit transform method if you only implement a transform one. So again, the idea is we have the base estimator, which we inherited from to get the basic functionality, and the transformer mixin giving us only functionality for the transformer. This can be used, for example, for the standard scalar to create different instantiations of the standard scalar as usual. Don't worry, we will have more examples later in this video. So let's go directly to one example of multiple inheritance with Python in general. Let's create one class, animal. And an animal is defined basically by a couple of things. Let's say here by the size. And we also set the amount eaten at the beginning to 0. We could make this a default argument in the initialization, but at this point I'm a little bit lazy, to be honest. Then every animal does two things. There are different things different animals do, but two things are there for every animal, at least I think. And this is eating, so somehow consuming energy, however, and pooping, somehow getting rid of something that accumulated in your body. So these methods are easy to program. We just say how much did we eat when we eat, and then poop returns the waste. So it's basically just like the size divided by 10 times the amount eaten, and then we set the amount eaten to 0 again because we are now gotten rid of everything we've eaten until now. That seems easy, okay? So let's now create a class. This is now the subclass, for example, like one example of it. A bat. A bat is an animal, so it gets all the functionality from the animal. Okay, and now we can look at it. We create Otto. Otto is our bat, and Otto eats 100 of whatever, and then Otto poops, and it's 20 of waste. Whatever these numbers mean, that's not important. This is all just a stupid example. Now there's an interesting thing. A bat can do more than just eating and pooping. A bat, for example, can fly. So how can we add now the flying functionality without putting it directly into the bat? Because there are other things that can fly as well. For example, a bird. Okay, how can we do it? With a mixin. We can create the flying mixin. Here we just say we give fly, the method fly, a distance which the animal has to fly. And then we just return the distance divided by the size of the animal, like of the thing that flies. That does not have to be an animal. And now the interesting part here is we just assume that whatever uses the flying mixin also has a size. And this is not provided by the flying mixin. This is one of the parts which can get tricky if you do these things yourself. But in scikit-learn, for example, you rely on the idea that everything usually has a fit method. Okay, so now I can create my bet and I just say it's an animal and it's a flying thing. And for example, just to give you an example, what could be a not animal but flying? An airplane, right? There you also want to have a flying mixin, then you define the size in it and it still works. Okay, now let's see. Everything we had before works as well. Otto can be a bat, Otto can eat, Otto can poop, and now Otto can fly. So this is an example of multiple inheritance using mixins in Python. Now let's look directly at scikit-learn. So how can you use mixins in scikit-learn? We talked about this before. Basically, for example, for the transformer, we can use the base estimator and then add the transformer mixin and get something that is a transformer. And there are other mixins as well. There are some for supervised models, for clustering, for feature transformations and selections. There are so many, I cannot list them all here, and there will be more in the future. And then there are even other scikit-learn compatible packages which provide you new mixins. And you can write your own, of course. Now, let's understand it a little bit better. Let's deep dive into the standard scalar. Or to be more precise, let's create our own standard scalar, which is a crappy version of the official one. Okay, so in practice, don't use this code, use the official scikit-learn standard scalar. What is the task? The task is, and I'm getting this information from Wikipedia, you can get it there as well if you want to, that we basically just want to take any x, so any data point, we want to subtract the mean, divide by the standard deviation, and then we get a standard scaled or z-scored value. So if we scale our sample with that, it will have a 0 mean and a standard deviation of 1. We want to add something else as well. We want to make it possible that you as a user can say what mean it should have. And for that, we just want to add another initialization method. So what do we have to do? Let's break it down. We will have to implement an initialization method, which basically saves the mean we want to have after transformation. We need a fit method, which will basically estimate the sample mean and the standard deviation so we can perform this transformation. And we need a transform method, which basically does this. Okay, let's do it. First, we import numpy as np just for some computations, and then, and this is important, we get the base estimator and the transformer mixer. In our next step, we just implement what we just discussed. We have standardizer with base estimator and transform mixin as the inheritance, so we have multiple inheritance using one mixin. Then we just save the mean after transform, usually it should be 0. And then we have a fit method following scikit-learn's templates, and then we just save the mean and the standard deviation. Again, we have a tailing underscore, so we show that these are fitted values. This is just a convention in scikit-learn, but it's good to follow it even in your own code. And then we just return self, so the object itself. And last, in transform, we just do the transformation I've talked about. So basically say x minus self.mean divided by the standard deviation, and then we subtract the mean after transformation. Now we can just have an example. We just define some x values, we transform it, and transform, and it seems to work quite well. So if you would mean that, it would get to a mean of 0 and probably also a standard deviation of 1. Basically, we can still get the params as usual in a base estimator. So get params works, set params works as well. Perfect. But now there is the interesting thing. Because we use the transform mixin, we can also say fit transform. And this is something we have not implemented ourselves. So we did, as you can see above, implement fit, we implemented transform, but we got for free get params and set params from the base estimator, and fit transform from the transformer mixer. So everything works, everything is fine. Let's get to a little bit more complicated examples. So basically, now we talk about models. In scikit-learn, models implement scoring. So it allows you to say .score, provide x and y, and get a score out of it. For this, we usually have at least two important mixins, which are regressor and classifier mixins. These help you to implement regression or classification models. There are also other things they add, not only the scoring method, but these are details we are not talking about here. But just that you know, it helps you to be compatible with other parts of scikit-learn without you having to think about it. And that's like one of the big advantages of keeping consistent with scikit-learn standard conventions and inheriting from their provided customization classes. Let's go for the first example, which is regression. For regression, we only have to implement, in addition to the base estimator things, a predict method. So let's look at an example. This is my dummy regression. This is something we've created in the last video. Basically, we just have initialization, we have a fit, where we just fit a median or a mean, because what we want to do is just predict the mean or the median for every value. And then we say predict, and there we just predict then always the mean or the median. That's it. So that's all this is doing. We have one regression model, which is a dummy model. So just to give you a baseline, which can fit the mean or the median and predict using this mean or median for every value. Now, if you look at it, we can, for example, create an X and a Y. We apply now our dummy regression. So we initialize it and we fit it. We get our dummy model. And now we can use a prediction to get a prediction, right? .predict. But if we say .score, it does not work. Why does it not work? Well, we only inherited from base estimator until now. And the .score came from the regression mixin. So let's also add this regressor mixin just from scikit-learn base. We just added here, has the same code as before, like nothing else changed. And now it works. Interestingly enough, like a regressor mixin usually implements the R-square scoring, which has as a default to give you 0 if you perform as good as a baseline model, basically. So it makes completely sense that we get a 0. So everything seems to have worked. Now let's talk a little bit about classification, because classification is a little bit more tricky than regression. Here, important methods to implement are predict and usually predict prober, predict log prober, or decision function. Can also add all. The interesting part here is that for classification, usually if you want to visualize it, there needs to be some sort of continuous value. And to get these continuous values, you usually use predict prober or decision function. But let's look into it a little bit more now with the example of the supported vector classifier. Importantly, I will not implement myself something here because then we get too much into details of implementation. And I just want to show you what a decision function is and what predict prober means. We just import it. Then we import some things for visualization. So matplotlib as PLT and Seaborn as SNS. And then we again create our new target. So we get the X from before and we just say we want now zeros and ones because this is a classification problem. So everything that's above 0 basically is a 1 and everything below and 0 is a 0. Now that we have this binary problem, we can apply the supported vector classifier. So we just fit it and then we predict and then we also save the decision function. So we have now saved the prediction of the supported vector classifier and the precision function. Let's print it out. Prediction 0, 1, 1. Okay, makes sense. Like it can only predict a 0 and a 1. And decision function are now these strange values. -3 point whatever, 1 and 3 point whatever. And if you look at it, it already seems to be something of an alignment between the prediction and the decision function, because that's the important part. The model uses the decision function to make a decision on what it predicts. So here, for example, you see all the positive values led to a 1 and the negative ones to 0. Here, I also try to visualize it. So basically you can see now the true labels, the decision function, and the prediction as colors here. And what you can see is we seem to be quite good in predicting, but the problem with the decision function is it's not really easy to interpret. Like what does a 3 mean? What does a -3 mean? This can be very dependent on the model you use. Like here, it is still interpretable to some degree, but like in other models, it's not. Because what is a decision function? Generally, it's just an internal function used by the classifier to determine which class it should predict. But here, for supported vector models, it basically is proportional to the distance of x to the separating hyperplane. So a supported vector machine always draws like a hyperplane, and then on the one side is one class, on the other side the other class, and so on. This makes sense to everybody who knows supported vector machines. For everybody else, don't worry. This is not about supported vector machines. This is about how this decision function works, and basically it just tells you it's some value giving you a representation of what should be predicted. As the decision function is not always easy to interpret, what if I want to do claims about the probability of x being of class 0 or 1? Well, for this, classifiers implement the predict proba, so predict probability. The interesting part for supported vector classifiers is they don't have it by default. What you have to do is you have to initialize it with probability equals to true, because not every classifier has to have the predict proba or the decision function. Usually they have only one of them or both. We can do it now. Predict proba. Predict proba gives us a probability for all classes. So you see basically the first column, the probability of being 0, and in the second column, probability of being 1. And now I just reduce it to the probability of 0, so it's a little bit easier to interpret. Also, like, it's 100% dependent, right? Like if it's 90% probability of 0, then it's 10% probability of 1. And we can print them out. And now if you look at it, it makes sense, right? Like the first value has a probability of 99% basically of being 0, and it predicts 0, and the other ones have very small values, so they predict 1. And you can see the same thing here in a plot, again the predicted probability, and now you can actually interpret this. So you can say for each value, okay, so probability of being 0 is under 0.4. And then at 0.5 you can see how it swaps the prediction. Okay, that was quite a lot, but actually everything was quite easy, because scikit-learn provides you an easy way to use mixins and therefore multiple inheritance to create things like transformers, regression or classification models. Thank you very much for your attention, and see you maybe in the next video.